blood, the average human possesses approximately 5 L of blood, a red, somewhat thick fluid with a pH of 7.4. Blood is pumped by the heart through the vessels of the circulatory system, transporting nutrients, signaling molecules, electrolytes, and oxygen to the cells of the body, and ferrying waste products and carbon dioxide away from those same cells to be eliminated by the organs designed for those tasks. Additionally, specific cells and formed elements of the blood travel in the bloodstream to perform their functions inside the bloodstream, or when they reach their destination, they leave the circulatory system and enter the connective tissue compartment to carry out their particular duties. Blood also functions in regulating the osmotic and acid-base balance and temperature of the body. Because blood is a fluid, it has a protective mechanism of coagulation, driven by platelets, which minimizes blood loss in case of damage to blood vessels. When 100 ml of blood is centrifuged in a heparinized test tube, it separates into its cells and formed elements and its fluid component, the plasma. The bottom 44 ml is composed of packed erythrocytes, red blood cells RBCs. The buffy coat, 1 ml composed of leukocytes, white blood cells WBCs, sits on top of the erythrocytes. On top of the leukocytes lies 55 ml of plasma. The bottom 44 ml is composed of packed erythrocytes, red blood cells RBCs. The buffy coat, 1 ml composed of leukocytes, white blood cells WBCs, sits on top of the erythrocytes. On top of the leukocytes lies 55 ml of plasma. The 44% of RBCs represents the hematocrit, the total erythrocyte volume. Blood cells and platelets have natural lifespans and must be replenished daily to maintain a constant number of each particular cell type in the circulating population. The process of this continuous renewal is known as hematopoiesis, hematopoiesis. Plasma constitutes 55% of blood volume, of which 90% is water, 0.9% is protein, 1% is electrolytes, nutrients and dissolved gases. The protein composition of plasma is presented in Table 10.1. The protein-poor fluid component of plasma leaves small venules and capillary beds to enter the connective tissue compartment, where it is known as extracellular fluid, interstitial tissue fluid. The protein albumin exerts a colloid osmotic pressure within the vascular system that is responsible for keeping fluid within the vascular system and limiting the extracellular fluid volume. When blood coagulates, some of the proteins and factors that are present in plasma are depleted during the clotting process. The straw-colored fluid that remains, serum, is a protein-rich remnant of plasma lacking fibrinogen. Formed elements. The formed elements of blood are erythrocytes, leukocytes, and cell fragments known as platelets, Fig 10.1. Special techniques and stains are used for the microscopic study of blood cells. Erythrocytes. Erythrocytes, RBCs, resemble biconcave discs and are the most numerous and smallest, 7.2 gm in diameter, of the blood cells, see Fig 10.1. There is a sex difference in the number of erythrocytes per unit volume. Women possess 4.5 x 10 RBCs per mm, and men possess 5 x 10 RBCs per mm. This number increases in both sexes if they live at higher elevations. In contrast to all other cells of the body, erythrocytes no longer possess organelles or a nucleus because they were extruded during their formation and before the time they entered circulation. Because of their shape, these cells have a high surface area to volume ratio, which assists in the performance of their function carrying and exchanging on for co and vice versa. To facilitate their ability to perform this function, these cells are packed with hemoglobin, and they possess the enzyme carbonic anhydrase. These cells preferentially release on and pick up co in regions of low on and high co tension. The tissues of the body pick up on and release co in regions that are oxygen rich and carbon dioxide poor. The lungs. Erythrocyte cell membrane. The cell membrane of RBCs, Fig 10.2, has the normal membrane composition of 40% phospholipids in the form of a bilayer, 10% carbohydrates, and 50% protein, which consists mostly of glycophorin A, one of the two transmembrane proteins, which forms part of the junctional complex of proteins that binds to spectrin ion channels. Carrier proteins, including the ion transporter band 3 protein that exchanges Cl** and HCO** ions across the cell membrane, permitting the erythrocyte to discharge Co in the lungs. Peripheral protein band 4.1, which binds glycophorin A to actin and tropomyosin supporting the plasmalemma, is a network of spectrin tetramers, proteins that form hexagonal scaffolding beneath the plasma membrane with the assistance of ankyrin, which binds spectrin to band 3 protein. Additional support of the spectrin scaffolding is provided by the junctional complex of proteins composed of band 4.1 protein, actin, adenosine, tropomyosin, and glycophorin. The supporting network of proteins provides not only a great degree of flexibility for the erythrocyte, but also an amazing stability and capability to resist shearing forces. These cells live for approximately 120 days, and during that time they pass tens of thousands of times through narrow capillaries where they become distorted and subjected to powerful shearing forces, but when out of the confines of these channels they resume their normal shape. The extracellular aspects of RBC plasmalemmas sport inherited carbohydrate groups that are antigenic and must be taken into consideration during blood transfusions. The two principal antigens are A and B antigens, giving rise to 4 blood groups, Table 10.2. Additionally, 85% of the U.S. population has one of the 3 principal Rh antigens, C, D, and E, and these individuals are said to be Rh positive, whereas the other 15% are Rh negative. See clinical considerations. Carbon dioxide and oxygen transport, RBCs transport Co and On by 2 different mechanisms. Most of the Co is carried as Hc3 ions, formed by the action of carbonic anhydrase on HO and Co forming HCO, that immediately dissociates into H and HCO*. In the lungs, where the Co tension is low, HCO** ions leave the RBC cytoplasm, and Cl** ions enter via the ion exchanger band 3 proteins. The exchange is known as the chloride shift. Oxygen is carried by the protein hemoglobin, a large tetramer. Each of the 4 polypeptide chains of hemoglobin is tightly bound to an iron-carrying heme group. Table 10.3 lists the major types of hemoglobin. The globin moiety of hemoglobin carries some Chi and is known as carbaminohemoglobin. It releases its Co in areas of low Co tension, the lungs. O picked up in the oxygen-rich lungs, binds to the heme portion, and hemoglobin becomes known as oxyhemoglobin and is carried to oxygen-poor regions where it is easily released. The place of O becomes occupied by 2,3-diphosphoglycerate, and hemoglobin changes its name to deoxyhemoglobin. Erythroblastosis fetalis, a possibly deadly condition for the fetus, is due to an attack by the mother's immune system against the fetus erythrocytes. During late pregnancy and at birth, it is possible for fetal blood to enter the mother's circulation. If the mother is Rh negative and the fetus is Rh positive, the mother forms antibodies against the Rh antigen. Initially, the mother produces IgM antibodies that are too large to cross the placental barrier, and there are no consequences for the fetus. Subsequent pregnancies may present complications if the fetuses are also Rh positive because the mother's immune system has switched isotypes. Instead of continuing to form IgM, it forms IgG antibodies against the Rh antigen. IgG antibodies are smaller and can cross the placental barrier. They bind to the Rh antigens on the fetal erythrocytes and cause them to undergo hemolysis, killing the fetus. To circumvent this condition, the mother is given anti-Rh agglutinins after the birth of the first Rh-positive infant to mask the antigenic sites on the fetal blood cells and prevent the mother from mounting a full-fledged antigenic response against the Rh antigen. The morphology of the erythrocyte is intimately related to its function. Mutations that cause alterations in the normal shape of RBCs may cause some types of anemia. Alteration in the polypeptide chain of spectrin may reduce its binding capacity to band 4.1 protein, and the spectrin molecules are unable to form a proper support for the erythrocyte plasmalemma, resulting in a condition known as hereditary spherocytosis. These RBCs cannot carry enough oxygen, and they are fragile and have the propensity to be destroyed by the spleen, resulting in anemia. Leukocytes, WBCs, number only 6,500 to 10,000 per mm of blood. They have no function within the confines of the circulatory system, they merely use it to reach their destination. When leukocytes arrive at their destination, they leave the capillaries or venules via diapedesis, migration between endothelial cells, enter the connective tissue compartment, and perform their function. There are two major categories of leukocytes, Table 10.4. Agranulocytes, leukocytes that do not possess specific granules, lymphocytes. Monocytes. Granulocytes, leukocytes that possess specific granules, neutrophils. Eosinophils. Basophils. Lymphocytes. Lymphocytes, round cells with an acentric nucleus that occupies most of the cytoplasm, are only slightly larger than erythrocytes and form 20% to 25% of the WBC population, see Table 10.4. Although they are agranulocytes, meaning that they do not possess specific granules, they have some azurophilic granules, which on electron micrographs were shown to be lysosomes. There are three types of lymphocytes. B cells constitute 15% of the lymphocyte population and are responsible for the humorally mediated immune response. They enter an unknown region of the bone marrow to become immunologically competent. When antigenically stimulated, they become antibody-producing plasma cells. T cells form 80% of the lymphocyte population and are responsible for the cell-mediated immune response. They have to go to the thymic cortex to become immunologically competent. Null cells compose 5% of the lymphocyte population and are of two types, stem cells and natural killer, NK, cells. Circulating stem cells can differentiate to form all blood cells and platelets of the blood. NK cells are cytotoxic cells that do not require interaction either with the thymus or with T cells to perform their function. Chapter 12 discusses the functions of B cells, T cells, and NK cells. Stem cells are discussed in detail later in this chapter. Monocytes, round cells with a kidney-shaped nucleus, are the largest blood cells in the circulation, see Table 10.4. Electron microscopy shows that these cells are rich in lysosomes and that they have a small Golgi apparatus, usually ensconced in the nuclear indentation. A few days after they are released from the bone marrow into the circulation, they leave the bloodstream, enter the connective tissue compartment, and differentiate into macrophages, constituents of the mononuclear phagocytic system. Macrophages, preferentially phagocytose dead and disrupted cells and invading pathogens, whether they are non-living antigens or microorganisms, release signaling molecules that induce inflammatory responses, and the proliferation of cells that act in the immune process can fuse with each other to form a very large foreign body giant cell that can phagocytose the large substance if the particulate matter is too large for a single macrophage. Become antigen-presenting cells that phagocytose antigens, break them down into smaller antigenic units known as epitopes, place them on their membrane-bound major histocompatibility complex antigens 2, MHC2, also known as Class II human leukocyte antigens Class II HLA, and present these protein fragments to immunocompetent cells. Inflammation is the body's response to noxious stimuli, which may include physical or chemical insults or the invasion of the body by pathogens. The initial vascular response is known as acute inflammation, and it serves to eliminate the harmful agents and begin the process of healing. If the inflammation is protracted, it is referred to as chronic inflammation and entails the recruitment of monocytes, lymphocytes, plasma cells, and fibroblasts, which attempt to ameliorate the conditions causing the inflammation. Neutrophils, polymorphonuclear leukocytes, polys, form approximately 60% to 70% of the WBC count, see Table 10.4. The nucleus of a young neutrophil has only 2 or 3 lobules, but nuclei of older cells become more lobulated, with each lobule connect to the main body nucleus, or to each other, by slim threads of chromatin. Frequently, nuclei of females display a small pouch-like bleb, or drumstick, housing the bar body, the second X chromosome that is believed to be inactive. The cell membrane of neutrophils displays Fc receptor and the complement receptor for C3b and L-selectin and integrins that facilitate adhesion to the endothelial lining in preparation for diapedesis. The cytoplasm of neutrophils possesses three types of granules, see Table 10.4. Specific granules, which are small and house pharmacologic agents the cell uses to destroy microorganisms. Azurophilic granules, lysosomes, which contain hydrolytic and oxidative enzymes. Tertiary granules, which house gelatinase, cathepsins, and certain glycoproteins. Chemotactic agents released by certain cells, such as mast cells, attract neutrophils to sites of acute inflammation, where they attack invading bacterial pathogens. To recognize the exit site from the blood vessel, endothelial cells, in response to interleukin, IL-1 and tumor necrosis factor, TNF, produced by connective tissue cells, display intercellular adhesion molecules 1 and 2, ICAM1 and ICAM2, to which the neutrophil integrins bind, stopping their travel in the bloodstream, and leave the blood vessel. To be able to enter the connective tissue and phagocytose the pathogenic bacteria, tertiary granules release the enzyme gelatinase, which digests the basal lamina to ease diapedesis. Neutrophils release enzymes from their specific granules to kill bacteria that invaded the connective tissue. Neutrophils phagocytose bacteria using their membrane-bound Fc and C3b receptors, Fig 10.3a and b. Azurophilic granules release their enzymes into the bacteria-laden phagosomes, Fig 10.3c. Specific granules release their enzymes into the bacteria-laden phagosomes that not only degrade bacteria enzymatically, but also kill them by the formation of superoxides as reduced nicotinamide adenine dinucleotide phosphate, NADPH. Oxidase acts on, initiating a respiratory burst that includes the formation of hypochlorous acid and hydrogen peroxide, Fig 10.3d. Neutrophils die after they kill the invading pathogens and, with the dead bacteria and extracellular fluid, form pus. Eosinophils, composing 2% to 4% of the WBC population, are large round cells with a bilobed nucleus. Their cytoplasm is packed with large, eosinophilic specific granules and azurophilic granules that resemble the lysosomes of neutrophils, see Table 10.4. Their cell membrane displays IgG, IgE, and complement receptors, and receptors for eosinophil chemotactic factor, histamine, and leukotrienes. Eosinophils function in destroying parasites and phagocytosing and degrading antigen-antibody complexes. The specific granules of eosinophils have two regions. Externum houses various hydrolytic enzymes and cathepsins, peroxidase, and histaminase, which limits the inflammatory response, see Table 10.4. Internum houses major basic protein, MBP, eosinophil cationic protein, ECP, and eosinophil-derived neurotoxin. MBP and ECP form pores in the pellicles of parasites to permit hydrogen peroxide and superoxides formed by eosinophilic enzymes to reach and kill the parasites. Basophils form only 1% of the population of WBCs, see Table 10.4. Their cell membrane sports high-affinity receptors for IgE, they have an S-shaped nucleus, and their cytoplasm is packed with dark specific granules whose contents include histamine, heparin, eosinophil chemotactic factor, neutrophil chemotactic factor, peroxidase, neutral proteases, and chondroitin sulfate. Basophils also have azurophilic granules similar to those of eosinophils. Although basophils probably are not related to mast cells, they have very similar functions because they both initiate inflammatory responses. Mast cell function is discussed in detail in Chapter 6. Mutations in the genes coding for ligands binding to selectins prevent leukocytes, such as neutrophils, from becoming marginate and from slowing down as they contact the luminal surfaces of endothelial cells. Normally, these ligands contact selectins displayed on the surface of endothelial cells. Because these contacts are reversible, the leukocytes do not stop but merely slow down. This condition is known as leukocyte adhesion deficiency. Macrophages in the connective tissue release IL-1 and TNF-A, which cause endothelial cells in the region of inflammation to express ICAM1 and ICAM2. Two of the leukocyte integrins, leukocyte function-associated antigen 1, LFA1, and macrophage 1, MAC1, adhere to ICAM1 and ICAM2, and the leukocytes come to a halt. IL-8, produced by inflammatory cells in the connective tissue, prompts the leukocytes to commit to diapedesis and leave the blood vessel to enter the connective tissue compartment. Individuals who present with mutations in the genes coding for the integrin molecules of the leukocytes have the condition known as leukocyte adhesion deficiency I, and some of their leukocytes cannot participate in the inflammatory response. Mutations involving the gene that codes for the enzyme NADP oxidase affect the ability of certain cells, such as neutrophils, to undergo respiratory burst response to pathogenic bacterial invasion of the connective tissue compartment. Although the neutrophils reach the area of infection and phagocytose the bacteria, they cannot destroy them quickly and efficiently enough to reduce their numbers to safe levels. Patients with this condition are mostly children, and they are said to have hereditary deficiency of NADP oxidase and present with frequent bacterial infections. Platelets, cell fragments 2 to 4 gm in diameter, Fig 10.4, see Table 10.4, are derived from megakaryocytes of the bone marrow and participate in the coagulation of blood and in the protection of damaged blood vessels. Platelets stay in the circulating blood for approximately 2 weeks and are then destroyed. Each platelet is discoid in shape and possesses a lighter periphery, the hyalomere, and a darker central region, the granulomere. Viewed with the electron microscope, platelets present a ring of 10 to 15 parallel microtubules, flanked by monomers of actin and myosin that encircle the platelet's perimeter. Two hyalomeres present two systems of cytoplasmic channels, Fig 10.41 that opens to the surface, a surface opening tubular system, that is an extension of the outer surface of the platelet, enhancing the surface area by a factor of 7 or 8. One that does not open to the surface, the dense tubular system. The granulomere viewed with the electron microscope presents peroxisomes, mitochondria, glycogen granules, enzyme systems that facilitate platelet metabolism and adenosine triphosphate, ATP, production, and 3 types of granules whose contents are detailed in Table 10.5, alpha granules, delta granules, gamma granules. The function of platelets is to quench blood loss from damaged vessels by forming a clot to plug the defect in the vessel wall. When the endothelial lining is violated and platelets contact collagen, they become activated and attach to the damaged area, a process known as platelet adhesion, and to each other, known as platelet aggregation. The process of clot formation depends on the interaction of various factors derived from the plasma, platelets, and damaged tissue. An undamaged endothelial lining releases nitric oxide and prostacyclins to prevent platelet aggregation and heparin-like molecule and thrombomodulin to prevent coagulation. The process of blood clotting involves a sequence of factors that act in a cascade where the formation or activation of one factor induces the formation or activation of another factor. The entire complex sequence of these events is not presented in this textbook, but is well described in many textbooks of pathology. The principal steps in blood clotting are as follows: damaged endothelium ceases to produce factors that prevent platelet aggregation and coagulation and releases tissue thromboplastin, von Willebrand factor, and the vasoconstrictor and endothelial cell mitosis stimulator endothelin. Platelets become activated because von Willebrand factor induces them to adhere to the collagen and laminin protruding into the lumen from the injured vessel wall, adhere to other platelets, and release the contents of their granules. Adenosine diphosphate, ADP, and thromboplastin released by the platelets increase their propensity to adhere to each other and cause the newly adhered platelets to degranulate. Plasmalemma of activated platelets produces arachidonic acid-derived thromboxane A, which constricts blood vessels and activates platelets. Platelets aggregate and acquire platelet factor 3 on their plasma membrane, facilitating the precipitation of coagulation factors. In the presence of coagulation factors, prothrombin is converted to thrombin, a reaction catalyzed by thromboplastin derived from platelets and the damaged tissue. Thrombin converts fibrinogen to fibrin, a calcium-requiring reaction. Fibrin monomers are cross-linked by factor 13 to form a reticulum of clot that, as it traps more blood cells and platelets, is transformed into a thrombus, blood clot. Within 1 hour, actin and myosin monomers released by platelets coalesce to form myofilaments whose contraction reduces the size of the clot and pulls the cut edges of the vessel closer to each other, reducing leakage of blood from the damaged vessel further. When the endothelial lining is restored to normal, plasminogen activator converts plasminogen to plasmin, a protease that, in concert with hydrolytic enzymes derived from platelet lambda granules, dissolves the heparin clot vitamin K, a cofactor in the production of prothrombin and certain clotting factors, is frequently present at insufficient levels in newborns, and they are usually administered an injection of this vitamin to prevent them from dying of hemorrhagic disease of the newborn. Infants who are breastfed and have not been injected with vitamin K are particularly at risk for lacking sufficient levels of this vitamin. Adults who have conditions that impede fat absorption may also be subject to vitamin K deficiency, which manifests as excessive bleeding and frequent bruising. The administration of supplemental vitamin K usually alleviates the disorder. Bone marrow, see Fig 10.5, a gelatinous, extensively vascular, cell-rich connective tissue, occupies the marrow cavities of long bones and the intertrabecular spaces of spongy bones and provides a microenvironment that is conducive for hematopoiesis, formation of blood cells and platelets. In infants and young individuals, all marrow is hematopoietically active, and because most of the forming cells are erythrocytes, it is known as red marrow. As an individual approaches 20 years of age, much of the marrow housed in the diaphysis of long bones accumulates so much fat that it becomes hematopoietically inactive and is known as yellow marrow. The marrow's vascular supply arises from arteries that enter the marrow cavity via nutrient canals. A system of large sinusoids that eventually deliver their blood into the central longitudinal vein, which delivers its blood into many veins that exit the marrow through nutrient canals. In contrast to most veins, the veins of the marrow are smaller than their arterial counterparts, and hydrostatic pressure within the marrow is high enough to maintain the patency of the sinusoids. The marrow's vascular compartment comprises the blood vessels and sinusoids, and the interstices are populated by clusters of hematopoietic cells, islands of hematopoietic cells, constituting the hematopoietic compartment. The adlaminal surfaces of the endothelial cells of the sinusoids are surrounded by a basal lamina. One fine mesh of reticular fibers. Two adventitial reticular cells that contact the basal lamina, covering most of the sinusoidal surfaces. Cytoplasmic extensions of these adventitial reticular cells extend away from the sinusoids and establish contacts with cytoplasmic extensions of other adventitial reticular cells enclosing spaces that house hematopoietic islands, hematopoietic cords. These clusters of hematopoietic cells are present in various stages of their development but most commonly are composed only of one specific cell lineage. In addition to the various maturing cells, macrophages are also present to destroy extruded nuclei, phagocytose discarded cytoplasm, and provide iron to cells of the erythrocytic series. Adventitial reticular cells control how much of the bone marrow volume is available for hematopoiesis. As they amass lipid in their cytoplasm, they increase in size and decrease the volume of the hematopoietic compartment. Hematopoiesis. Hematopoiesis has a prenatal and postnatal component. Prenatal hematopoiesis begins around the 14th day of development and has 4 phases. The mesoblastic phase is initiated when blood islands form in the yolk sac. Cells at the border of the blood island become endothelial cells, forming blood vessels, whereas most of the cells differentiate into erythroblasts that form nucleated RBCs. The hepatic phase replaces the mesoblastic phase at the end of the 5th week after fertilization. RBCs are still nucleated, and leukocytes begin to be formed at the 8th week after fertilization. The splenic phase begins during the 4th month of development, and the spleen and liver continue their hematopoietic function until parturition. The myeloid phase, bone marrow phase, starts around the 6th month of development and increases in importance as the fetus reaches parturition. After birth, all hematopoiesis occurs in the bone marrow, although the liver and the spleen can resume hematopoiesis if necessary. Postnatal hematopoiesis begins at birth and continues throughout the individual's life and produces an inordinate number of cells. An individual's bone marrow manufactures and replaces 1 billion blood cells every day through the process of hematopoiesis. Stem cells, the least differentiated of the hematopoietic cells, undergo cell division to form more differentiated cells, known as progenitor cells, which also proliferate to form precursor cells. Table 10.6. Stem cells and progenitor cells do not have histologic characteristics that differentiate them from one another. Precursor cells can be identified as belonging to a specific cell line, however, and each cell is identified by a specific name. Some precursor cells are able to proliferate, whereas others are post-mitotic cells even though they continue to mature to become a circulating blood cell. The process of hematopoiesis is closely monitored and controlled by cytokines and growth factors. Stem cells, progenitor cells, and precursor cells. The antecedents of all blood cells and platelets are stem cells, known as pluripotential hematopoietic stem cells, PHSCs, that reside in the bone marrow, forming approximately 0.1% of the entire nucleated cells of the marrow, and resemble lymphocytes. Although PHSCs seldom enter the cell cycle, occasionally they experience sudden spurts of mitotic activity, forming more PHSCs. Although stem cells are morphologically indistinguishable, they possess differing cell membrane markers that permit them to be recognized. PHSCs differentiate into two categories of stem cells, see Table 10.6, known as multipotential hematopoietic stem cells, MHSCs. Colony-forming unit granulocyte, erythrocyte, monocyte, and megakaryocyte cells, CFUGEMMs, are responsible for the formation of progenitor cells that give rise to the myeloid cell lines. BFUE, burst-forming unit erythrocytes, gives rise to CFUE and then to erythrocytes. CFUMeg give rise to megakaryocytes that form platelets. CFU eosinophil give rise to eosinophils. CFU basophil give rise to basophils. CFUGM give rise to CFUG and CFUM, cells that give rise to neutrophils and monocytes. Colony-forming unit lymphocyte cells, CFU-Li, are responsible for the formation of progenitor cells that give rise to the lymphoid cells lines, CFU-LT, T lymphocytes, and CFU-LYB, B lymphocytes. In contrast to stem cells and progenitor cells, precursor cells cannot regenerate themselves, i.e., they cannot produce more precursor cells, but they do possess definite histologic features permitting their identification as the predecessor of specific circulating blood cells, Fig 10.6, see Table 10.6. The first precursor cell of each cell lineage is proerythroblasts, which give rise to erythrocytes, megakaryocytes, which give rise to platelets, myeloblasts, an exception to the rule because they are recognizable only as the precursors of neutrophils, eosinophils, or basophils. Promonocytes, which give rise to monocytes, naive T lymphocytes. Naive B lymphocytes. Myelofibrosis is a condition in which fibroblasts of the bone marrow manufacture an abundance of fibrous connective tissue, instead of producing just slender collagen fibers to support the blood vessels, sinusoids, and blood islands of bone marrow. As more and more fibrous tissue is formed, the marrow becomes heavily inundated with this fibrous material, and the volume formerly available for hematopoiesis is reduced to such an extent that erythrocyte formation is reduced, and the patient becomes anemic. WBC formation may decrease or increase, whereas platelet formation decreases. This rare disorder, affecting 1 out of 50,000 people in the United States, is usually limited to individuals 50 to 70 years old. Frequently, this disease has no known cause. Idiopathic myelofibrosis, or it may accompany other bone marrow disorders or bone marrow infections. Many patients with this disease have been exposed to ionizing radiation or benzene. In its early stages, myelofibrosis is asymptomatic and remains so until the patient becomes so anemic that he or she experiences a decline in energy levels, loses weight, and has weakness and general malaise. If the leukocyte and platelet counts are also depressed, the individual becomes susceptible to infection, petechiae, and hematomas. Because the bone marrow is incapable of sustaining normal hematopoiesis, the spleen and liver begin to assume the function of blood cell formation, and they both increase in size, causing abdominal pain. The only way to confirm that the patient has myelofibrosis is by obtaining a bone marrow biopsy specimen. Patients with this disorder may live for 10 years or more, but in certain cases the disease progresses rapidly, acute or malignant myelofibrosis. There is no cure for this condition, although bone marrow transplants have been successful in ameliorating the disease. Hematopoietic growth factors, colony-stimulating factors. Certain cells of the body produce numerous glycoproteins that stimulate hematopoiesis. These hematopoietic growth factors, colony-stimulating factors, reach their target cells as endocrine hormones, paracrine hormones, or via cell-to-cell contact. Each of these factors stimulates a specific stem cell, progenitor cell, or precursor cell to proliferate or differentiate or both so that the level of a particular blood cell attains its normal concentration in the circulating blood. Table 10.7 Steal factor, stem cell factor, granulocyte monocyte colony stimulating factor, IL-3, and IL-7 induce PHSC, CFU-CEMM, and CFU-Li to undergo mitosis to maintain their population density. Granulocyte colony stimulating factor, monocyte colony stimulating factor, IL-2, IL-5, IL-6, IL-11, IL-12, macrophage inhibitory protein Ti, and erythropoietin induce PHSC, CFU-CEMM, and CFU-Li to give rise to progenitor cells, see Table 10.7. Additionally, colony-stimulating factors induce unipotential precursor cells to form neutrophils, eosinophils, basophils, and monocytes. Erythropoietin induces the formation of erythrocytes, and thrombopoietin induces the formation of platelets. Steal factor, produced by stromal cells of the bone marrow, is expressed on the plasma membrane of these cells. For PHSC, CFU-CEMM, and CFU-Li cells to become activated, they must contact the steal factor in the stromal cell plasmalemma. Hematopoiesis can occur only in areas where stromal cells express steal factor on their membranes. If hematopoietic cells are not contacted by hematopoietic growth factors, they enter into apoptosis, die, and are eliminated by macrophages. Erythropoiesis, granulocytopoiesis, monocytopoiesis, and lymphopoiesis. The formation of erythrocytes, erythropoiesis, requires two forms of progenitor cells to produce 2.5 x 1011 RBCs on a daily basis. If the number of RBCs in blood is less than the normal amount, endothelial cells of the kidneys, peritubular capillary network, and hepatocytes of the liver release erythropoietin. This factor, in concert with steal factor, IL-3, IL-9, and granulocyte macrophage colony stimulating factor, stimulates CFU-GEMM to differentiate into numerous BFUE, which proliferate to form even more CFUE cells. When these cells are formed, the kidney and liver cells cease the production of erythropoietin, and the low level of this factor induces the CFUE to form proerythroblasts. The cells of the erythroblastic series and their properties are presented in Table 10.8. The formation of granulocytes, granulocytopoiesis. CIS, depends on CFU-CM, which gives rise to two other progenitor cells, CFU-M, responsible for the monocyte formation, and CFU-G, responsible for neutrophil formation. Eosinophils and basophils arise from CFU-EO and CFU-BA. The factors IL-1, IL-6, and TNFO induce the release of the growth factors granulocyte colony stimulating factor, granulocyte monocyte colony stimulating factor, and IL-5, which function in stimulating the formation of neutrophils, eosinophils, and basophils. The first morphologically recognizable cell of the granulocytic precursors is the myeloblast, and the second is the promyelocyte. Neither myeloblasts nor promyelocytes possess specific granules, however, and all three granulocytes share these precursors. The next cell in the lineage has specific granules and can be recognized as a neutrophilic, eosinophilic, or basophilic myelocyte. The cells of the neutrophilic series are presented in Table 10.9. The progenitor cell of monocytopoiesis bipotential CFUCM, which gives rise to the unipotential CFUM, from which promonocytes are derived. These give rise to monocytes that enter the circulation. Platelets are derived from CFU-meg, which give rise to megakaryoblast that enlarge by undergoing endomitosis, where the cell undergoes mitosis without cytokinesis and gives rise to very large cells, known as megakaryocytes. These large cells lie next to sinusoids and extend their cytoplasm into the sinusoidal lumen. The cytoplasmic projections undergo fragmentation along demarcation channels and release proplatelets into the sinusoids. The proplatelets disperse into individual platelets and enter the circulation. Lymphopoiesis begins with the stem cell CFU-Li, which gives rise to the progenitor cells CFU-Lyt and CFU-Lyb. These cells give rise to naive T cells, CFU-Lt, and naive B cells, CFU-Lyb.